Hey, and welcome to our next session, which will be Introduction to Ceph and how to use it for CloudStack. As a speaker, we have Danny Abukalam, who is a product engineering lead at Softtime, and Danny will tell us a little bit more about how to use Ceph and CloudStack together. Hey, Danny, it's your turn.
Thank you very much, Yvette. So yeah, as you said, I'm Danny, and today I'm going to be delving into the open source project Ceph. I suspect that many people in the CloudStack community are already familiar with Ceph, but for those of you who aren't, my goal is that you'll have a basic understanding of its internals by the end of this presentation. And I'm fairly new to the CloudStack community, but I'm also going to cover how Ceph integrates with CloudStack, and I'm hoping I can rely on others in the community with more experience to help me if I get stuck. So to start with, I'd just like to give you a bit of background on, so I run product engineering at Softtime, and we manufacture and build hardware and software solutions for the data center. And our flagship product is called Hyperdrive, which is a fully supported on-premise Ceph appliance. We're over 60 people now, and we've raised more than $40 million in funding. And one of the key things you'll notice here is that for a company of our size, we have offices covering almost all working time zones. And this allows us to support our customers at any time of the day. So, Ceph, what is Ceph? Ceph is a software-defined storage platform. It's fully open source, and it has a strong global community of developers and users, primarily operators of large clouds and storage clusters. So what does fully open source mean? It means that not only is the source code available upstream, but all the collaborative development happens in the open as well. It's a big project with many different code bases, which for the most part are GPL. Some other licenses too there. Ceph's primary design goals are resilience, flexibility, and scalability. So data integrity and consistency is the first and foremost priority. We never want to lose data. So for those of you that are familiar with CAP theorem, that's consistency, availability, and partition tolerance. Ceph is CP. So when things go bad, Ceph will choose to go down first rather than incurring data loss. And it's very flexible. It provides us with a set of interfaces that allow us to interact with the storage cluster from lots of disparate environments, address the cluster as objects, block storage, or as a file system. Another primary design consideration is scale. It's been designed from the outset to scale without paying any performance penalties. So we do this by scaling our infrastructure horizontally rather than vertically. The other thing that's really important about Ceph is that it's self-healing. It's really very, very good at keeping itself healthy as long as you follow some basic best practices. So even when steering off course and going off piste a bit with new and unstable features, it's really hard to lose data unless you break some very fundamental deployment rules. So what is software-defined storage? I'm going to cover this first because at the heart of it, really, this is the problem that Ceph's trying to solve. So bear with me for those of you that are already very familiar with this paradigm. If you look at a traditional storage architecture, you can imagine that way back when we had a single computer, we had some disks on it, and that was good enough. We had a client that would address, read, write to the disks through a computer, all is good. The client really likes this, and so he tells his friends, and all of a sudden you have a lot more clients, and they're using the same computer and disks. And this holds up for a certain amount of time, but then suddenly you have way more clients, and then you need to have way more disks. And then you also need to have a bigger computer as well. So you end up scaling not only the disk, but the computer itself. And this is called scaling up or scaling vertically, which is a strategy that's broken for many reasons. It's inflexible, it's very hard to manage and support, and it only scales to a certain point. So I'm not sure this is, this is the founding principle upon which Ceph is built. Instead of scaling vertically, we want to scale horizontally, and this is all software-defined storage is like this. The idea is that to minimize the amount of resource we have behind a single logical node and have lots of heterogeneous nodes, and ideally address them in parallel on a network. We can then add and remove nodes as we need to. We can lose multiple nodes, and we don't really care. And it's a much easier system to support, manage, and maintain than larger monolithic systems. While SDS allows us to worry less about our hardware, we found that hardware is still very important. And Ceph excels when good choices are made around CPU, network architecture, drive-to-node ratio, memory, and many other areas. We've also found that Ceph excels when you have consistent hardware. So this is what's led us to take a task-specific appliance approach to Ceph. We'll talk a bit more about that later. So underneath everything, at the heart of Ceph lies something called rados, which is the Distributed Object Store. It stands for Reliable Autonomic Distributed Object Store. And above this, we have libranos, which is a set of libraries that allow us to interact with the rados system directly. And above this set of libraries, we have three interfaces, RBD, RGW, and CephFS, which are each projects in their own right. But ideally, essentially, the objective of these projects is to provide you with different flexible interfaces, block, object, and file. So there's a number of daemons that make up a running Ceph cluster. And the most important ones are the four that I've got on this slide. It's actually a lot more than this, but these are kind of the core daemons. So OSD is the first one, and this stands for the Object Storage Daemon. It's a central daemon that runs on our media nodes, and it receives the read and write requests from rados. Best practice is that you usually will have a single OSD daemon for each physical drive. So, if you have 10 drives, that's 10 OSDs. There are some exceptions. If you're doing some crazy performance stuff, sometimes you'll have more OSDs per drive or multiple drives in OSD, but typically you'll always have an OSD for a drive. This is kind of the centralized service that is running. So if the OSD is down, that usually means that you're not going to be able to read or write from the hard disk, and it might mean that your hard disk is down or something else. The monitor is how clients authenticate to the cluster. And this is the thing that keeps the whole Ceph cluster up and running. It manages all the other daemons, and these are highly available, and they use the Paxos algorithm to elect a leader between each other. So you always want to have an odd number, usually a minimum of 3 in a production cluster. But 5, 7, 9, depending on your architecture. We typically recommend running daemons on dedicated hardware, and we have a dedicated monitor node ourselves for this purpose. We also try to spread these across different failure domains, such as different racks or cages. And I'll talk a bit more about this in a bit. The manager daemon is a recent addition to Ceph, and by recent, I mean a couple of years ago. It's a new daemon which aggregates much more detailed metrics from all the other cluster daemons, and it provides an API which allows you to write pluggable modules to interact with the cluster, monitoring, management, that kind of thing. It's a neat and tidy separation layer, and it's what we use for our storage manager, which is our dashboard. That's the API that we use to manage and monitor Ceph. Finally, you have the RDS Gateway, which is a RESTful HTTP server, completely stateless. You can spin up as many as you like, and it just does the right thing. Primarily, you can use this to spin up an S3 compliant service and consume the Ceph cluster entirely over S3. It scales really well, incredibly fast, especially with large object sizes. It also supports Swift API if you guys are familiar with OpenStack's object storage. But yeah, not so much anymore. It's mainly S3. So data placement, how are we going to get stuff in and out of Ceph? Traditional storage systems have this concept of controller nodes that keep our write journals and tell us where everything is. This clearly doesn't scale because controllers need to maintain coherency amongst each other, and we have an additional hop every time we want to make a request. So not great. Modern distributed storage systems have a different paradigm, and they use something called calculated placement to avoid this problem, and Ceph is the same. It uses calculated placement. So in Ceph, this is called CRUSH, Controlled Replication Under Scalable Hashing. And essentially, what we do is we generate a map of all the devices in our cluster. And then we also generate a policy set for our data placement, which we call CRUSH rules, which essentially tell us how we want to write stuff to the cluster. And this is fairly easy. You get a default set of CRUSH rules when you build a Ceph cluster, but then you can make more policy changes to say, hey, I want to put this set of data on this fast set of drives, or this set of data on this slow set of drives, or whatever. It's very flexible. So what we do is we take the map of the cluster, and then we take this set of rules and we combine them, and then we the monitors then distribute these to any of the clients that are connected to the cluster. So when clients want to write data, they take their data and they hash it against this the cross rules that they've received, and they will get deterministically get the same location in the cluster every time. So this means that clients are always able to read and write directly to an OSD in the cluster without any additional questions or controller nodes or anything else. So we expose all of our devices on the network, and then the client just talks directly to those devices rather than having to go through any intermediary thing. And so we call this being cluster aware. There's another concept in Ceph which is pretty useful, and this is placement groups. In reality, when we write to OSDs, we're actually writing to a placement group. And placement groups are an abstraction layer above the OSD, which form part of how Ceph deals with different storage tiers, disk sizes, disk failure, and it's what allows us to specify different application schemes on a pool-by-pool basis. Without placement groups, in the case of a disk failure, we'd have to recover by writing a whole disk's worth of data to a new and empty disk, similar to RAID. Very slow, very ineffective. With placement groups, instead, when a disk fails, we can just rewrite additional copies to lots of other disks in the cluster, which is much quicker and far more effective. Not nearly because we're also writing this additional copy from lots of other disks. We're not writing it from one source. So, when we have a failure and recovery, we're basically writing tiny bits of data from the whole cluster to the whole cluster. So it happens very quickly. Very, very neat and tidy kind of recovery process. Placement groups used to be pretty strict and fiddly in early versions of Ceph, but they've come a long way and they're now quite flexible and much more easy to use. There's a basic formula you can use to get a good placement group number for your pools, and there's calculators online that can help you figure out the right numbers. Also, in recent versions of Ceph, you have this thing called the PG autoscaler, which will automatically try to determine an adequate placement group number for you on the fly. So next you have Erasure coding. So by default, every pool in Ceph is triple replicated. So this means we store 3 copies of all of our data, and it means that we aim to have at least 2 copies of the data at any point in time, even if the drive fails. So this is kind of necessary to ensure that we don't lose data. Data loss is quite hard, even if we're super unlucky and lose 2 drives with the same data on them at the same time. The problem with this approach is that it's quite expensive. So we always need 3 times the amount of raw storage as usable storage. So in order to get 1 usable petabyte, we're going to need 3 petabytes of raw storage. So Ceph's answer to this is Erasure coding. If you're familiar with RAID 6, this isn't a dissimilar concept, although it's more flexible and a lot more complicated as well. But you don't need, it doesn't expose all this complication to you. It's fairly simple to use, but it just the underlying mathematics will definitely make your head hurt. So rather than storing 3 copies of an object, instead, what we do is we use polynomial mathematics, and we plot the data that we want to write on a curve, and then we break that object down into a set of data and parity shards. We then store these shards across the cluster, and we can afford to lose the same number of shards as we have parity shards and still restore our data. So on this slide, the example is a 3+2 erasure code profile. So we write 3 data shards. You can see A, B, C, D, E, F, G, H, I. These are our data shards. And then we generate 2 parity shards, which are the 4 and 5 shards that you see here. We then write these 2 different OSDs, and we can afford to lose up to 2 shards and still generate our data again. Ceph has a pluggable system for erasure codes, so you can actually pick and choose your favorite profile or write your own if you really want to. It can get very complicated, but there's different erasure code profiles which are good for different things. But the main thing you need to note is that you just want to ensure that your erasure coding happens at a host level. So each shard is spread across a unique host, And in most cases, that means that you need a minimum number of hosts to effectively benefit from erasure coding. So a big enough cluster. We typically find the magic number is around 9 or 10 nodes before it starts being sensible to use erasure coding, and then you get all the benefit of cost savings and storage. And the other thing to note is that you don't necessarily have to do this cluster-wide. You can do this on a pool-by-pool basis. So you can have some pools that are erasure coded and other pools that are triple replicated, and you can have specified different erasure coding profiles across these pools. So very flexible again. Right, so RBD. This stands for rados block device. And what this allows us to do is create images which we can present as virtual block devices. And essentially what this is doing is taking the virtual disk and striping it across objects in the rados cluster. So you can think of it a bit like AWS's EPS in kind of architecture. And it's really flexible, and we can use it across a whole number of different environments. We can use it straight into any Linux host. There's a kernel driver called KRBD. It's mainline in Linux, and it allows us to map an RBD image into a local client block device, which we can then just mount. The beauty of RBD is that for virtualization environments such as CloudStack and others such as OpenStack, Proxmox, OpenNebula, whatever the virtualization you want to use is, you can mount RBDs as the host drives when you boot a node. So for you guys, using CloudStack, this is pretty handy. This is done with librd, which has mature plugins and drivers for the majority of these hypervisors, and you can live migrate machines between computer hosts without worrying about where their local storage is. Ceph's mature driver support in all of these virtualization systems is a killer feature, and it's one of the things which means that Ceph has really widespread use. It's also very well tested. So you can use the kernel driver known as KRBD to consume RBD images into Linux, but you can also use it with things like Kubernetes pods. There's a native Kubernetes driver as well with support for RBD in the container storage interface. RBD has lots of snazzy features. Primary amongst these are snapshots and clones. So a snapshot is a read-only point-in-time view of an RBD image. Clones are writable, and the system will only store the delta. So, for example, I would provide a snapshot of a base Ubuntu OS image, and then every time I create a new VM, the base image will be a clone of that base Ubuntu snapshot. Except the clone is, of course, writable, resizable, renameable. So snapshotting and cloning is done near instant and is very efficient, and it leverages the underlying support for copy on write in rados. So clones don't use data until I write something different to them, which is pretty efficient. RBD also has a journaling feature, which allows us to keep track of changes to RBD images in a separate pool, and this is mainly used for mirroring RBD images across different clusters. So that's pretty handy if you want to have different Ceph clusters, but you want a specific image to be mirrored. And you can have quotas for RBDs, and you can have namespaces, so it has tenancy support. And you can have a trash function as well, which will keep deleted data around in the cluster for a specified time. So kind of like a bit of an immutability kind of thing going on. So that's RBD. Probably the main thing that's relevant to CloudStack, but there's also file and object, which I want to talk about a bit, just to give you the context and make sure I've covered Ceph. CephFS is a distributed network file system. It's POSIX compliant. It allows concurrent shared access to the file system from multiple clients, and it's come a long way in recent years. Has lots of cool new features that have been added in most recent versions of Ceph. We get the same scalability and performance as any other Ceph interface by separating the data and metadata pools. And essentially, we have a data pool that writes data just like we would a normal rados call, but then we also have to keep track of all the POSIX semantics and metadata in a separate pool in parallel. And we avoid overhead by having a stateless daemon, which is called the metadata service, the MDS, which we can then scale out. It's also stateless to lots of nodes, and these will carve off different parts of the file tree automatically based on demand, which is very clever, balancing themselves to try and eliminate any bottleneck on the fly. So if all of your clients are using one specific folder, then the MDS is going to, if you have 4 MDSs, it might just use 3 MDSs to service that specific, to store the metadata for a specific folder, and then the rest of your entire file tree might just get, 20% of a single MDS. So it's pretty clever how it balances I/O that way. All of this is stored in its own MDS pool, which you can put on, for example, a faster tier of storage. It handles all the cache coherency between the MDSs and locking and stuff. So different clients connecting to the file system are always up to date with the changes, and you don't have conflicts and issues. Ceph also supports snapshots, and unlike most distributed file systems that support snapshots, you can also take a snapshot of subdirectories within the file system, not just a snapshot of the whole file system. So that's a pretty cool feature. The RDS Gateway, which is the final interface, this is a stateless HTTP daemon, and it provides S3, also Swift, but not so relevant anymore. Has full support for multiple sites and multiple namespaces or tenancies. It's super scalable and performant on our nodes. A single storage router, which is where we put our S3 gateway, achieves line rate S3 performance with RDS Gateway. So it's really good from a performance perspective, and it can be scaled almost infinitely. So you can just spin up as many of these as you want, and just they become endpoints, and they just address and translate the S3 requests into rados calls. And so typically what people do is they put a load balancing layer in front of these, which then handles SSL termination and then sometimes other functions like rate limiting. And this also has support, so you could run S3 as your own service. If you're like a hosting provider, you could run S3 and then figure out how much each one of your customers are using and build them accordingly, and integrate with or external authenticators such as LDAP or OpenID Connect. So it has a fairly full and kind of featureful, mature feature set. So recent releases of Ceph. How am I doing for time? I think I'm doing okay. I'm pretty trying to fit this all in half an hour. So Ceph was first conceived in 2006. First stable release of Argonaut was 2012. So we're approaching the 10 years of stable Ceph releases. Pacific is the most recent release, released this year. It brought with it a few new features, including a new deployment model around containerization, a new RESTful API, the ability to have multiple Ceph file systems, Ceph support Windows, which is pretty cool. And just in general, the last few releases have focused on usability, trying to make Ceph easier for new users, less complicated from the outset, even though under the hood it's a very mature kind of storage operating system. So it's about trying to make this easy to use, even though it's pretty cool under the hood. So yeah, that's recent releases of Ceph. Just want to point out we have our own dashboard for Ceph. So it's a kind of a managed UI system which you can use. It focuses on kind of the hardware side of things as well. So it gives you the ability to completely manage and tear down not only Ceph from itself, so you could redeploy Ceph. It has, but it also has the ability to bare metal provision the nodes and redeploy them as well. So that's a pretty killer feature. It just means that people without command line experience can easily manage and administer the cluster and keep an eye on cluster health. The manager also allows you to keep track of node and drive health, and helps if any deeper issues arise, such as temperature increases or gives you access to remote console. This is all made possible because we ditched traditional BIOS and BMC paradigms, built our own BMC platform, which uses modern APIs to expose and abstract key hardware functionality. So now that you're all familiar with Ceph, how can you integrate it into CloudStack? Well, there's a whole host of ways, because it's pretty flexible, and turns out CloudStack is pretty flexible as well. I've talked about RBD and how we can use the block device interface. And the first and most obvious integration is to use that with KVM to attach Ceph into CloudStack. So we can specify RBD as a primary storage, as you can see on the right. As long as our network is configured correctly, CloudStack will handle the RBD image creation and the mount on our behalf. It will do the right things in libvirt to keep the RBD pool mounted across all of your libvirt agents. And once we've added our Ceph cluster into our CloudStack deployment, we can then create disk offering specs with certain sizes, and we can use them to create new volumes, which we can then attach into VMs directly. So that's the primary storage RBD kind of use case. But with Ceph, there's also a number of ways to get an iSCSI target. And so you could also theoretically just use iSCSI to mount into CloudStack as primary storage as well. And then you have secondary storage in CloudStack, which is S3 and NFS. And you could use Ceph's S3 target for that, or NFS on top of CephFS with Ganesha. And you could use that as a secondary storage. Finally, I haven't played with this, but I've kind of read about it, is that the CloudStack has this built-in service that lets you deploy Kubernetes, the Kubernetes service. And there's a Kubernetes through CSI is completely cluster aware with Ceph. So you can directly spin up persistent volumes based off of Ceph RBDs with the CSI plugin. So if you're using CloudStack to deploy Kubernetes, then you can very easily connect this to Ceph RBD and back your Kubernetes cluster with Ceph, which is pretty cool.
Danny, as we're approaching the end of the time, I would like to stop you for a second so that we can go through the few questions which we have, as we have quite a lot of questions on the chat. Sure. I will start with the first one. Is Ceph a viable platform as backing storage for latency sensitive applications or applications that require high I/O throughput? It seems like writing the same data 3 times might affect latency or I/O. Is this correct?
Yes, definitely is correct. Of course, you're going to have more latency using Ceph's OSDs than you would a local storage, because Ceph prioritizes data integrity. So when I write something to an OSD, I have to wait for that OSD to then write it to other OSDs and then come back to me and confirm those writes. So you do have higher latency than local storage. That's unavoidable. But Ceph does a very good job of trying to minimize that latency. The secondary writes are done in parallel. And this is something that's had kind of optimization over time. If you have very fast network and a very fast I/O backplane, you can minimize this. So it depends on the workload, it depends what exactly the latency requirements are as to whether or not you will be forced to use local storage.
And what about, are there any news on management multi-monitors with CloudStack for RBD?
Sorry, say that again?
The question is coming from Samuel, who is asking any news on managed multi-monitors with CloudStack for RBD?
Any news? I don't know. Don't know the answer to that question.
Maybe Samuel, you can get in touch with Danny, you can chat with him and give a little bit more specific for the questions, and I'm pretty sure that Danny will be able to answer after the talk. Going to the next question, how viable is running Ceph with Replica 2, and how likely am I going to run into a race condition with quorum?
So there's two different questions. Rep 2, just don't do it. Like, please don't do it. Just don't do it. It's always a bad idea. We see it all the time. And we see we do support through we do a lot of Ceph support with customers, and it's always people with tears in their eyes and crying to just don't bother. I can see why it's an attractive idea, but there's reasons why Ceph does triple replication out of the box. So best practice deployment is to use triple replication. As for monitors losing quorum, that the only time that I see that happening is where you have so like a multi-site split brain connection between monitors, where you end up with an even number of monitors that are unable to elect a leader. So I think I've never seen that, but I think it's always important to figure out where you're placing your monitors and make sure that you think about where your points of failure are going to be in the network to make sure that you always have an adequate number of monitors in the cluster.
And according to you, how does the Erasure coding performance compares to the replication, and how it behaves during drive failure compared to replication?
So that's a good question. The thing about Erasure coding is it's very flexible. So you can, there's a whole host of different profiles you can choose. And your choice of profile will massively affect the performance that you're going to achieve. In some cases, you can get better write performance than triple replication with Erasure coding, because you're writing more shards essentially, so it's spread across more disks than it would typically be with triple replication. But there's definitely a CPU overhead to recovery, and so if you choose something insane like I don't know, like a K of 22 and an M of 1, then yeah, you're going to have a hard time. I think what we typically advise is to, before going into production, have a number of different pools, have a number of different profiles that you select, and then to test not only writing and reading to those pools, but also a recovery scenario, so that you can see what kind of performance you're going to achieve with those different profiles that you've selected, and then how that compares to triple replication.
Thank you, Danny. As we already run out of time, please take a moment, Danny, to spend some time in our virtual lounge, and I'm pretty sure a lot of people would like to talk with you. And for everybody who has any questions, you can just chat with Danny or book a meeting through the CloudStack Collaboration Conference platform. Thanks once again.
Sounds great. Thank you for having me.